blades. It's just how I did it. I'm not an aircraft engineer, but the way I did it allowed me to run a full RPM test without any dynamic balancing. It's all static balancing of the rotor system. So I thought I'd share how I did it. For demo purposes, I'm using this blade that I made. This is my first attempt at making a blade. It was too heavy, it was too large on the cord, and so I changed the design, but for demonstration purposes I'll be using the blades that I made in the beginning. The first thing we need to do is find out where the center of mass is on the blade in respect to the cord. So we need to know, if I was to push up on my finger, where would it balance along the cord? So what I've got here is a piece of angle iron, and it is laid down at 45 degrees to the straight edge on my table. I've now placed the blade on the angle iron, level with the edge of the table, where it balances. Notice the blade grip is still on the blade. This needs to be on, as it can affect the balance of the rotor blade, and of course when it's spinning around all together, it needs to be taken into account. I've now chocked the blade so it can't move, and what I'm going to do is place a straight edge in line with the top of the angle iron. Do this looking down from above, and I'm going to draw a line across at 45 degrees. I've drawn my line at 45 degrees now. I'm going to turn the angle 90 degrees from where it is now, rebalance the blade and draw another line. This is now where the center of mass of the blade lies. So we can now measure how far back the X is from the leading edge and see where we are. Our cord length is 180 mm. Our centre of mass is 56 mm back from the leading edge, so if we divide 56 by 180 times by 100, we get 31.1% cord mass. Our goal is 25%. That is for a 0012 blade, so we are too far aft, and this can cause problems like blade fluttering, and also the collective. If you've got a collective pitch helicopter, then it can cause issue with too much force going for the collective. So 25% is where we want to be. There's a couple of things we can do to get this balance right, and that is, one, we could add weight to the nose, or we can reduce weight after the blade. So if I cut more out of this section here, that would bring the weight forward, and that would get our blade cord mass further forward and closer to where we need to be. But we need to bear in mind that when we're reducing this section, we're also reducing the strength, and our centrifugal force is going to go up or down according to what we do. Next thing to do is the span balance of the rotor system. So what we've got is a tube, and that is full of water. The tube goes along to the other side, same thing, and as we know that water in a tube will level itself either end, provided there's no air bubbles in the tube, so make sure there's no air bubbles. And then we can see that I've set this water level about 12 mil on the rule, both sides.
Чому більшість новачків йдуть з трейдингу, тільки не почавши? Вони покладаються на успіх, а раптом вийде.
And the rotor blade is sitting between 30 and 35 there at the moment. What will happen is when you're walking around, you create air movement, and you actually the blades will teeter up and down very easily, so you've got to walk slowly around it and make sure there's no air being blown from outside or whatever. So we've got 35 on that side and we've got 45 on that side. If we now add 2 M6 washers, we'll watch and see if it levels out. Okay, after 5 minutes of bobbing up and down, I'd say that was around 38 mil, and 38, 39 mil the other side. That is our rotor balanced. I'll just show you it was only teetering on a single bolt, bit of box section, and 2 M6 washers is what it took to balance it out. The last thing we need to do is find out if the rotor system is balanced as a whole in the chord direction. What I've got here is it balanced on a bolt on a single piece of rounded flat bar, so it can tilt where it wants to. I've then got a digital protractor, inclinometer, place that on top, and then we can see that it isn't level. We need to shift the rotor left or right to get this to read 0, and then we can measure this distance from that point to that point, and we can use these shims to insert down there and shift the whole rotor to one side so that it's balanced in the center. It's now balanced as close as I can get it. If we have a look, we've got a bigger gap that side than we have that side. So it's off to one side. So we can make small adjustments to lead and lag the blade, and that will make a difference to the rotor balance. If we can't do that, then we'll just have to add shims to this side, so that it spins on the axis that balances. I hope that's been of some help to people, mad people building their own helicopters. From the blade mass you can then determine the centrifugal force on the blade. Once you know that, you can work out the coning angle and therefore the undersling on the teeter hinge. But we'll leave that for next time. Thanks for getting to the end. See you again.